Continuing on the safety factors, and the first lecture we talked about the definition, and I started going through some examples, and then that was about how far we could get. Today we're going to continue with a couple examples. I want to talk mostly about different ways to look at and know the demand on a product. And I mean, one of the reasons I'm doing this in the context of factor of safety is to show that depending on how you are conservative in determining the demand, your result will be different. As far you won't need as much of a safety factor. So the safety factor that we talked about was the failure load over the allowable load. Failure load, we said, will vary depending on manufacturing, the quality control, and the design itself. So there is some uncertainty there unless you do a very, very precise and accurate design. For the allowable load, a lot of times it's more dependent on the application. So if it turns out your structure is being used in ways that was not supposed to be used, an example of that is, say, a car elevator. So if you go in a storage garage where people can go and put the car for the winter, you have the elevator instead of having a ramp, to go between floors, like at the airport, for example. So each car comes in, gets to this floor, and goes out a little bit like we do for just a regular passenger elevator. And if somebody comes and puts the same weight as a car, but on the one side of the elevator, it's not something that's accounted for in the design. The code that governs the design of the elevator says you can only put the weight, you don't have to put the weight further than, say, halfway on one side. So you have the middle, you say, I'm going to put all the weight halfway as opposed to put it on the edge, because you have to come with, lead shots. If you really, or in that case that we were looking at, somebody came with a forklift, fully loaded. That was much light and much smaller wheel span, so they were able to put all the load on one side as opposed to more or less in the middle, and that came to be a problem. So, is it fair to assume people know that this is, to load big things as opposed to very small, heavy things? It becomes more of a design question. But by the time that I ask for something that I know I need to load in the middle, then obviously if I load it to the corner, I don't have my safety factor anymore. Actually, I can fail some of the devices that take care of eccentricity. So if this is loaded on the piston, you have railing to prevent it from turning. That railing is only so strong, depending on how much you say in your design that you're going to allow the load to be off-center. So it's very simple in the first place, but you can start with an assumption that turned out not to be true all the time when people don't use your structure the way you thought they would use it. So the other definition with the yield stress and the working stress is very similar, and it's actually even more unclear to me as far as working stress. Although when we were talking about the ASME last week, saying it has a very high safety factor, but it's based on the main value of the pressure as opposed to include pressure variation from closing valves, from pressure water hammers, or everything you can have. So we could probably argue that ASME works with the second definition, where even by design you know that you will exceed your working stress sometimes. Demand capacity. So the two examples I will talk about trailer design, which I did and I built. And then I'm going to talk about cars or ATVs, so kind of automotive type design, which in both cases, there are no real codes. So if you go through the literature, nobody will tell you exactly how to design a trailer or a car as far as strength. It will, the passenger car standards tell you you have to put so many lights at this height and all these characteristics. You need redundancy in your braking system. There are a lot of specifications, but when it comes to decide how big the frame needs to be and how it gets connected and how it gets tested, the manufacturers are more or less left on their own to make sure that it's strong enough. So that's pretty much the topic for today. So we don't really have a code or standard, but we're going to talk about looking at ways to look at loads applied and capacity. So it's a relatively simple frame. I'm going to draw it. So it's two beams that are 8 foot long on each side. Rectangular beams. And then in the middle, I have the tongue that goes about halfway from the middle going forward. It's also a beam. So these have cross members here. I'm just going to do it at diagonal. There's a cross member here, and there's some members here for the floor and to hold everything together. So single wheel, we'll put it here on a torsional suspension, so that doesn't make that much difference, but anyway. So the way to design this, you can start from the bottom up, because those wheels, if you start with a single wheel, you can only put so much load on them before you start just wearing the tire or heating the tire. So in this case, they were rated for 1,000 pounds each. So single axle, 1,000 pounds. Are you going to put the whole load on one side of your trailer? Probably not. But that's where, in my case, I said that would be my safety factor. So I'm going to put 1,000 pounds on that beam and make sure it doesn't deform permanently in the middle. And you can't have too much of a multiplication factor here because of the suspension. So there can be some multiplication, but say I allow for 500 pounds here and 500 pounds here. That'd be balanced by this. That gives me the size of this member. And I can only buy these beams by increments of 1/2 inch or 1 inch in size. So there's a point where, well, one is not really good enough and the other one is a little bit bigger. So I end up with, the little bit bigger. So in this case, this one is 3 inch across. And when I come to do the other side, well, it's the same size. This member here gets loaded if I end up putting the weight a little too far towards the front of the trailer. And in practice, even if I've done the design by using it, I've been using this 8 years now, and I know if I put the weight here, then instead of all going into the suspension, some of it goes on the ball, so I can put a little bit more weight. So when I designed it, I think I put the weight right around here, and that made this member here too weak, the cross member, if I was not changing it. So the way I ended up strengthening these two in the middle because of possible added force loading this way. And that's all based on essentially not following the rule. The rule is you're supposed to have 90% of your weight on your wheels and 10% on the tongue. But it's not always going to happen, so I ended up putting more here. I had to straighten this cross member, this cross member. These two, they don't really do anything. So they are smaller in my design. In the bottom line, if I think of this as being a steady load, that's all I would need. But in practice, when I go through puddles and into the field, it's going to have to resist also some torsion. So if I have more weight in that corner, this is going to bounce, and the plane of the trailer will try to wreck. And that's something that becomes a little more complicated to evaluate, but talking to people that have been building trailers for a long time, they told me as long as I make my welded connections at the corner, that'd be more than sufficiently strong to resist the torsion. Yes?
They may not have known the term racking.
Yeah.
For a structure like this.
So we start as a plane. It's 8 feet by 4 feet. So say the size of this board, a little bigger in this way. And instead of staying as a plane, if this wheel's pushing up very quickly, it will try to move up here, and this one wants to stay this way. And the only way you're going to prevent this deformation of your floor is by the resistance of the connections at the corner in tension or bending.
Basically, it's twisting as the bed.
Yeah.
Okay. But it's called racking, right?
So I went by their history, mostly because I thought it was going to be really hard to decide exactly how much force to put it here and how much inertia, because it's an inertia issue. It was going to influence the transfer of the force from one side to the other in a dynamic manner. And at the end, I know it's not really oversized because at some point this location deformed a little bit. But I put on probably about 3,000 pounds in it instead of 2,000 pounds at some point. I was not going really fast, but I knew it was all full of firewood, essentially. Not the full height, but to a decent height. And after I went back and checked. The reason why I didn't get concerned with the overload is in this connection here, I did not have welds on the tension side. I designed my connection so essentially this member was sitting under the cross member and the welds were on the compression side. So if I try to draw it, it'd be the cross member coming, and well, let's do it this way. So it'd be coming right under and being welded together there, and on the sides. There's some stiffening plates there, but the idea is where I knew there was a risk of a tension yielding, there are no welds at all. And that tension yielding is something that in my case happened once. And that's how I know that I don't have any crack or any significant deterioration of that member. But it would be a lot easier to design this in ways where you put some more welding, essentially. And if you have welding in the tension zone and you start deforming it, then you're at risk of a premature failure depending on how the weld quality was. So I decided to put aside the uncertainty about the capacity of the metal by not having the connection where my highest stress was. And I'm glad I did it, because otherwise I don't know exactly what I would do with this trailer at this point. I'd probably have to stiffen it from under in some ways. The idea that, for example, if we look at it, this is the frame, so you can see over here in the middle that the main member here is going under, because when I load this up, it wants to push, and this one wants to go up. So that's why I want to have the cross member on top here. That's really where the load is the highest, at the front cross here. This is how big it is today, and I know that if I lent it to one of my friends, they're going to put something heavy in it. They need to be aware they can't fill it up. If you fill this up, you're going to have, you can put maybe 4 tons of dirt in this trailer easily. And it's only a 1-ton capacity trailer. So it becomes common sense. I mean, there are things to look for, because just here where the fenders are, when you go above 2,500 pounds, you go through some bumps and the wheels hit the fenders. So you know you're getting close. And I had to raise them at some point because I wanted to put a little extra. But it's really custom design, and I can't say, that I'm going to go and sell these things, because you need to know, exactly how it came about. To be like a much longer user manual than something that you're supposed to go to Sears and buy built and get on the road with. But I started more or less from scratch, and then I looked at what others would do for the same situation. When it came to the upper portion, I ended up finding ways to make it lighter than most covered trailers. So I have some composite beams. I don't think we see the inside, but it's a composite structure here with U-shapes going all around. I have diagonals. There's a very high safety factor for the whole thing to take off, because I've put enough steel that's connecting the roof of this to all the way down. But at the same time, there's not as much safety as far as starting to deform it on the way back in a ductile way, because of the redundancy, the amount of steel and bolted connection that go between the lower frame and the upper frame. It will bend over. It will not take off. And that was pretty much my design criteria. In addition of saying, okay, so I have 2,000 pounds in it, so if I start lifting the roof and it's for whatever reason there's enough suction to take 2,000 pounds, well, I don't want the whole thing to take off, so it's got to be able to take 2,000 pounds of pulling force. So we can fill it up and lift it until the wheels untouch the ground. Just with the idea that I didn't want to deal with all of the aerodynamic issues. I mean, there's some basic aerodynamic calculation I did where at the front it has a pointed nose, but say it had a square nose. The baseline calculation, if you're going to ride 65 miles an hour, is you assume a force of 25 pounds per square foot for the wind pressure, and it gives you a good idea. If I have 25 pounds on this panel here, I'm looking at least, so 4 by 4, 20 times 25. So I'm looking about 500 at least pounds just pushing on it. And you can double it because you don't really know. I mean, am I really going to stay only into 65? Probably not. And then you have some effect of wind going around the truck and hitting the the trailer. That's not taking into account in that simple velocity calculation. So that's pretty much the idea for the upper. Just I actually went stronger in strength, but it's still a relatively flexible structure, and that's why it also has a cross member two-thirds of the way, so there's no issue of side forces, which are a little bit like the lower frame. How much side forces are you going to have? You don't know. So there's a cross member in the at the beginning, and at 1/3, and the door in the back also prevents from racking. The same type of twisting of the overall fuselage. Yes?
Did you look at fatigue loadings too?
No.
Okay. Did they not fail in fatigue, or?
Oh, no, there's no failure on it, even though I abused it.
Oh, he's asking, did you design for it?
No.
You just ignored it.
No. So by taking the worst case load here and not putting welds with the safety factor, it includes the factor of 2 reduction due to fatigue. So I didn't, when I said I had a safety factor of 2 because I put the whole load on a single beam. That sort of included the long-term material properties. But it's not, it's still designed as an extreme load scenario with the idea that that extreme load is more than 60% of the working load that would generate fatigue.
Another way to think about it is, if you were to look at the structural welding code, the design allowable stress is only half of what your minimum yield stress is going to be. So you've already got a factor 2 safety on the members, but the design allowable stress for the welds is only 30%. Okay? You have a higher factor of safety on the welds. He's saying by not putting the welds in tension, he didn't have to worry about that. The code doesn't tell you that, but this is one place where the code's conservative. They can't control whether something's in tension or compression in the design. He can as the designer. Plus, he doesn't come under anything. He can kill himself with this trailer. He's allowed to. Okay, no, seriously, most of the laws state you can build your own airplane. You just can't fly anybody except your immediate family. Okay, you can kill your family, you can't kill anyone else. If you start to fly anybody else, then you come under a different standard of the FAA.
Yep.
So he has a factor 2 safety inherent by using the design allowable stresses from the codes. That gives him a factor 2 on the members. He got around the problem with the welds by putting them in compression rather than tension. If you can always do that, you can't always do that. Right?
No. So it's a very good question, but it does bring the general concept. Like when we go to ASME and you design your pipe with a certain working pressure, you don't go and say, well, my pressure is going to vary, so I'm taking it down further. It's already built into those values that are there for shutdown and ramping up. Now, it doesn't mean that if you cycles multiple times per day that it's necessarily part of that application. That's what you need to check for. But in my case, the other aspect is I'm dealing with structural steel, no welds, and I'm doing a design so it doesn't yield. That's how I started. Well, for fatigue, if I wanted to break this in, say, 10,000 cycle, those beams here, without welds, I will have to go beyond the yield point. That's what it will take to break under those conditions. So we're not in a condition we call high cycle fatigue, where you have millions of loading cycle. It's only when you hit a big bump on the road that there's really something going on here with strength, that you have some dynamic factors that add and could result in getting close to the yield strength. Now, in retrospect, well, that's where, when I talk about practical design, this member here, if I wanted to optimize it, and this was a race car, I would make it thicker here. Actually, I did that because I made the tongue longer after I built it. It started as a 12-foot member, and I made it to 15 feet. So in the end here, it's a smaller beam. A transition from a bigger beam to a smaller beam. Mostly because I decided to make it longer after I had it. But the idea is, when doing this is a lot more fabrication. Everything here is a lot more fabrication. So if I start changing the section size as I'm moving along, I'm adding the number of pieces of metal to put together. I could do the same here. For this member, the highest load is in the metal. I could say I'm going to strengthen this section. But it's not always practical. I mean, in the end here, I only had beams, and you saw them on the floor, and I wanted to put them together. I didn't really want to have to make longitudinal connections or lap joints just to optimize everything as if it was an airplane. It's not an airplane. So the practical way to make this stronger is to make the whole beam stronger. And that's why you become heavy very quickly. And that's how I analyzed this, I arrived very quickly to the conclusion I had this soft point right there, and maybe here up above, but I didn't have any welded connection there either. I had some welded connection underneath to hook up the suspension, but not on top. So that's a little bit how I came about doing this in practice, and I overestimated the demand based on what I could put into this, and looked at other similar designs that people have done. It worked out. So in terms of looking at what could happen in a process, and I'm taking the trailer example again. If this was going to be built by somebody else after I came up with this design, I have to be very clear that there can't be any well where I decided there was not going to be any tension well. It looks very obvious, but we've seen cases people have ladders that on the drawing it just says a 24-foot ladder, and then it turns out somebody put some welds in it because they only built it out of 16-foot long members. And there wasn't any requirement for the quality of those welds. It just made them the way they thought it was going to be okay. And it came out to be a very big problem. So in terms of fabrication here, no welds in my tension zone. And the inspection of the welds was mostly the welds that were going to prevent the twisting of the floor. And if I didn't have any weld, I used bolts to connect top and bottom. But if I had welds there, they'll have to be very well inspected because they were going to work in tension or shear, maybe, depending on what the design is. And when I talk about service history, well, it was my first one. And that's why I didn't want to pretend like I knew everything from the basic principles. So I did go and see, sizes of trailers of about the same capacity to make sure that I wasn't far off. And I looked at what I couldn't account for, the torsional effect, what kind of strain I would need for that. Now we're going to go to a little more complicated structure. So we're looking at an ATV, quad, or four-wheeler. What we're going to talk about for the front suspension here is more or less applicable to cars as well. I mean, it's obviously slightly different, but the idea is they have what they call the control arms. So we're looking at the wheel here. It has a knuckle, that is holding the wheel and the hub system, so all the bearings are built into this one component, and you hold that knuckle with 3 points. This ball joint here is for the lower frame, or the lower control arm. You have a little ball joint here, that's the tie rod that goes to the steering wheel for holding sideways. And you have another ball joint on top, right here, to go into the upper control arm. So these are the only 3 ball joints that are holding the knuckle, holding the wheel. In this case, we see that the suspension is attached to the lower control arm, and therefore we know that one's going to be loaded more. Not because the only thing you can do with the upper ball joint, what happens is you have bushings here and you have a ball joint there. So it will only prevent the wheel from tipping back and forth. And it's the lower arm that's going to make sure that that the wheel doesn't, that the suspension doesn't collapse, that it stays on the ground. So the lower arm is supporting the ground force, which actually is not that much. If you look at the shape of the arm, it's an A-frame, we call, or it's a triangle anyway. And therefore, it's stronger for forces that are back to front as opposed to up and down. So we're looking at that frame with the ball joint. So for a force hitting an obstacle or applying the brakes, you can resist it by a combination of tension in this member, compression in this member. So it's more or less of a joist or a truss structure. For a force coming from the ground, say this way, and that's resisted by the suspension we're going to put right here. This is the 2 tubes individually working in bending to resist the ground force. So if you design this, you have to think about both of these factors. How much force is going to come from applying the brakes as opposed to how much force is for resisting the load from the ground. And maybe you're going to hit you're going to have some wood logs or stones that you're going to hit with that member right here. You can see they're putting a little fender, little protection here that goes on top here. So there may be some dirt, some grass that will also hit this member. It's a complex loading, and when you think about those rubber wheels going around a rough terrain, you can arrive to worst case scenarios. It's be really hard to put more than the whole weight of the vehicle on one wheel, because if you start really putting a whole lot more than that, it means you're landing really fast on one wheel, and that would typically get you to lose control. There's only so much worst case forces that you can think of here for vertical load on that ball joint. And same for applying the brakes. If you arrive to a certain force for this, then what you need is a friction factor against the ground. And that will give you, a good idea for this load going backward. And as far as a load this way from turning, it's a little bit the same story. If you turn your wheels, there's only so much you're going to engage with the ground. Maybe it's a friction factor of 1 in the worst case scenario, but most likely if you're on the road, it's going to be 0.6, 0.7 for rubber. So you can work out these 3 forces. I don't know exactly how you handle the question of hitting some stones and wood pieces. And that's why they do a lot of field testing. So they hire people to go out and they put force transducers. They are mounted right between the hub and the wheel itself to capture all the vertical, torsional, and shear type of forces between the hub and the wheel for different driving conditions. And then you can go back to this type of analysis or to a fine element analysis and evaluate how close you are to these worst case scenarios and how often they show up. Because we didn't talk about this yet, but as compared to my trailer example, here you do have welds. You can't make this complex shape. These are hollow tubes with ball joint forgings and everything together in a practical sense without welding them or using a lot of rivets or bolts. And the rivets or bolts are too expensive for this application, so it ends up being a lot of welding. And when we're talking about welding, then the fatigue becomes more important, and that ties into, again, in our first example. So we want these to be low enough. We want the strength to be sufficient to handle these worst case scenario loads for, and that's where also the history comes in. How many times would you expect somebody to ride it to its limit? And there's no really single answer. What I would say from working with these types of devices is even when you take these worst case loads, the safety factor is still very high because they don't want the wheels to come apart just like that. It's designed to be taking a high amount of abuse. Now, it doesn't mean, and that's where some of my work comes in, doesn't mean if you run into a tree that it will still be the same after. You become into a crash situation where we're not talking about these forces. Now all of a sudden this force just went way up on the and the whole unit spinned around, and at that point you could think of it as a good thing if it's absorbing energy because you really exceeded what you can tolerate for handling by a lot. That's where you want your design to be. You don't want to be loading it in a condition where you're still in control, going around a curb with a car, and all of a sudden something deforms and you lose control. You want this to be able to sustain it as long as you're on your wheels and you're not in a rollover or skidding situation. But at the same time, you can't make it in such a way that if you drop it from 20 feet off the ground, that it's still going to be in the same condition. It's a little bit how it works out. I think you can see it's not completely random. In other words, you can tell that there's been a lot of years of experience knowing you want to spread these members instead of having just one piece coming out to take into account the back and forth force from applying the brakes. That's why it's spread into an A-frame as opposed to just a piece sticking out. Now, I would say for the upper arm, this one, and you can see it on this graph, the spreading between the two members is less. So it becomes tighter here because when you're further from the ground, you don't have as much of that back and forth force. If we're looking, this is the ground. You have the two ball joints, and that's the knuckle. So the force ultimately comes from the ground, say, backward. What this ball joint needs to do is to resist it by about twice as much, and then you reach equilibrium with about half the load on the upper one. And that actually shows up in that design. It doesn't really come from testing. It comes from that simple analysis of moment. And if I try to do the same, for the size of this member as opposed to this member, I end up with similar characteristics. If I'm looking at that knuckle here, what I've seen lots of times is they make it stronger on this lower half. Sometimes it's just twice as wide, so you know exactly that it's stronger as opposed to this half, because they know that it's not going to have to resist the same loads. A combination of worst case scenario loads, field testing, and material testing. Now, once they've taken all of this into account, they don't have, if you go to fatigue for this, you don't have a safety factor of 4 anymore, because you've looked at it enough that you can tell it's not going to go much beyond your calculation. And it's the same for manufacturing. They make the welds in segments. So if you have a weld around a round member here, this one comes into the frame. They weld around in segments. And if we think of it, if you have one that's not done correctly by mistake, you still have three-fourths of your circumference. And that could be one way to look at it when you're saying, what would be my worst strength? Well, maybe I got one that's not done right. And still be able to, it will still meet your requirement. Not that you want that, but because if you say we're going to do it for 3/4, then maybe you're going to end up with only half that's welded. But it's the kind of, it's our way to make sure from the manufacturing standpoint that you have the strength that you expect. If I go and say, for my design, I'm going to take the strength of 3/4 of it, I'm going to ask for 4/4, no question, in the shop. But when it comes to really what would be unacceptable, this will still be acceptable as something that happens. And from the loading scenario here, this is not really how I want people to drive my product. Need to put it in because I know that people abuse it to a certain extent. And that's working when we talk about working with the capacity. That's the capacity and that's the demand. And the more you know from history about the two of them, or field testing, the more you can reduce that factor of safety. And I've seen some ways of calculating the useful life of these products that will go essentially and say a safety factor of 1. Because they've put it all in here, they put it all in there, and they put a lot of cycles of this, and that's it. That's all you get. If it can resist all these loads for so much time, taking the worst manufacturing case into account, and you have all that service history to verify that these loads are worst case scenario by putting sensors on your unit, then it's a little bit like your example with the landing gear. Your safety factor is just going way down. And one of the reasons you do that is you make a lot of them. And if you can make them 20 pounds lighter, 25 pounds lighter, I mean, they do handle better. If you get stuck in the snow, you can more easily take it out. So it's still a situation where not everything is optimized, because these tubes are typically the same length all along, even though this one is loaded in compression, and you would want to have it, more resistant to buckling, for example, the way I drew it. But it's not practical. You're going to build out of straight tube. So instead, they have some cross members that will help against the buckling capacity and all of this. And that's another thing we haven't really got into each member, but they all have a very specific criteria that you have to design against. If you want to take the weakest point of this, it would be a competition between a well that's too small here and maybe this member being a little bent to begin with, something like that. And that's where you will start figuring out your design. Calculations, testing, yeah, I like you to think about this in demand and capacity as far as safety factors. So if you know what it's going to be used for, if there's maintenance, are you going to drill some holes in your tubes? I mean, it happens in big structures. I worked on the erection of big structural frames for nuclear recovery systems, and the contractor came and put in some tubings for just conduits for the electrical into the main frame that had to be resistant to seismic deformation. So the design of the member was to work in plasticity back and forth. And if you have holes in it, it's not the same. Now, what of the problem there was now it's done. So what exactly are we going to do about it? The whole structure is there. They have walls. They have a roof. And this guy came and drilled some hole. Well, the first thing I said that everybody first was very surprised was, well, don't plug weld them, because you're actually going to make the situation worse. Welding will add residual stresses to your situation to the point where when you get the plasticity, you're going to be more likely to initiate cracking than if you do nothing. So one way, these were rounded holes. One way we thought we could do is just sort of elongate these holes in this shape. That would be for loading this way. So we don't have as much of a stress riser at this location. Professor Eager talked about factor of 3 here. We can take it down to 2.5, and that's for elasticity. When you get to plasticity, it's less, the stress concentration factor. But anyway, we could work on that geometry. What we ended up doing was to apply a stiffener that was welded away from the strengthened zone. It wasn't an easy fix, because it's the same situation where you have the code with all the requirement and the built-in safety factor, and now no matter what you do, you're not getting to what exactly you wanted in the first place. So you have to re-evaluate all the situations. If I stiffen the hole, so I have a plate like this with the hole, and I come and I just put another member that I weld here and here, I don't want to increase the stiffness too much of the system, because it's still supposed to work by deforming back and forth. It needs to have compliance and energy absorption. That's the design requirement. So we did find a way, but it wasn't to say, well, let's make it look the same. Because in terms of property, that was really the worst case scenario. Yeah, we talked about the design situation. So, so the safety factor, the number you see, 4, 2, 3, is not really meaningful unless you put into the context what exactly is the load you're looking at, the demand, and what exactly is the capacity. There will be an acceptable rate of failure when we're talking about cars, a crash situation, obviously, and there may be other situations where really you abuse the car. It's 20 years old, and the suspension just hit the bottom so many times that it can't take it anymore. So I think that's be fair to say I'm going to design it with a suspension. If I go and say every car that comes off the road, I want to design it so it's fine for 20 years, even if the suspension is busted, that may not be practical. You may end up with a heavier car. There's always going to be variation in your capacity, and mostly when we talk about bolts, welds, any kind of connections is something that will reduce your capacity, and the variability of that will depend on your inspection. We haven't talked about that a whole lot. We'll do at the next class. So after going through this, and I think you know the answer, we don't design things much stronger than they need to be at the very end. So when we see factor safety of 2, factor safety of 4, it really doesn't mean you can put 4 times more demand on your structure. It's just that there are things that are variable that you know about, not that you're really ignoring them, you know about, but you haven't gone through the process of quantifying them. And that's fine. What's actually important is to be able to be consistent. So if you're making the design of a car in a certain way, and your history tells you it's strong enough, you can keep doing it this way and keep, because you have your built-in history. You may be able to optimize it gradually, but you have to keep watching to see that you're not getting beyond what's acceptable in service. If you're relying on the service history a lot, you have to keep track of it in a more detailed way. Any question? Any comments?
I got a couple of comments.
Go ahead.
If the students don't. This idea that you've got at the top of putting the welding compression, it's pretty fundamental. And I had a case down in Florida where a guy had built design. A hunter decided to go into the business of making tree stands. These are little stands that you put up in the tree, and you can sit up there and wait for the deer to come by and shoot them, or the turkeys. Actually, turkeys are harder. Anyway, they put the weld on the tension side. They didn't put it on the compression side. And the weld, if it had been made properly, would have been big enough for the strength. It had probably a factor of 3 if it had been made properly. Well, it wasn't made properly, and the guy fell down his tree and died. Okay, so the idea of how you place your, I mean, you talked about designing your trailer. Well, I had the exact same thing in a tree stand. It killed the guy because someone didn't think about, if you have a choice, if the loading is going to be this way, you put the weld up here so it's in compression. You don't put it this way so that you're pulling right through the weld. Okay, when you're loading this way, your 2 members are just pushing against each other, and base steel has less variability than the other steel. You asked a question about fatigue. Just in general, the codes, whether it's ASME actually has higher factors of safety, but structural welding code has on buildings a 1.67 safety factor, and on bridges a 2.0 safety factor. That 2.0 basically assumes high cycle fatigue. You know the SN curve. Okay, you want to draw an SN curve in the other scoring?
Yep.
Anyway, that's for the members. The welds you assume will have defects. They won't all be made perfectly. The SN curve for steel, there's a 50% of yield. You'll have infinite life. And Dr. Belmar was saying, well, he knew he wasn't going to go to millions of cycles. Okay, so he could actually could have an even lower safety factor because his actual stress that's going to cause yielding is going to be much higher. And the code has already given him a factor of 2. Okay, so if he's designing low cycle fatigue, you actually have your safety factor is even more conservative, but they use the factor of 2 for fatigue for bridges and buildings. Anyway, I'll talk about some of the other stuff later. I did have, hey, I sit here and listen to it. I can think of other things. I'll talk about. He talked about bolting on trailers, the big heavy trailers tractor trailers going down the highway. You are not allowed by code to weld on that frame, that steel frame. Too many trailers have fatigue at the weld. You can only bolt. Okay, but we'll talk about that. Bolts are heavier. They're not as strong as welds. Why do we do it?
It's long to do.
It has to do